to show you some ideas for teaching some of the more difficult ideas to do with forces and energy at Key Stage 3.
Jifty Chugg, the science consultant for Barnet LEA, has brought in Steve Hearn, a head of science and a network coordinator for the Institute of Physics, to help some of her science teachers who are physics non-specialists. One of the teachers taking part is David Crossley, on a Teach First scheme.
David Crossley is a teacher who's been recruited on this Teach First scheme, which is to recruit high-achieving students with good background in education and good degrees to teach in challenging schools.
I don't feel very confident teaching physics, no. I feel fine with biology and with chemistry, but physics, I understand it myself. It's explaining the concepts to the pupils that I find difficult.
Today, Steve is looking at forces, a topic which most non-physicists find difficult. He starts with a homemade air bazooka to show how unbalanced forces result in acceleration, and follows this up with an investigation into how air bubbles rise in glycerol. And he shows us how force arrows can be used to represent the forces acting on a body.
It's a piece of drain pipe with a T-piece which goes through a hose to a vacuum cleaner. To fire the bazooka, I'm going to turn on the vacuum cleaner. I'm going to put a piece of paper over the end of the tube. The projectile that I'm going to fire is just 2 squash balls and some duct tape, a little bit of sellotape to make a very loose seal around a toilet roll tube. Forces and energy are almost the bête noire of any physics teacher who doesn't have a physics degree, and even physics teachers that do have a physics degree struggle getting these ideas over. They are, in essence, simple concepts, but they require quite a high level of abstract thought, and obviously, certainly with Key Stage 3 children, you're asking quite a lot of them unless you take things slowly and you have many strategies that you can bring into operation. OK, you start to see the paper pulling into the tube. I can hardly hold it, and away it goes.
The next step for Steve is to get the teachers to explain how the bazooka works using force arrows.
So what I'm going to get you to do now is on your whiteboards there, just to sketch a picture that you might use to explain to a Year 9 class the forces involved in causing these objects to move. OK, let's have a look at some of our drawings. Let's begin with yours, Kelly, and you can just tell me what you've drawn there.
I've drawn the little thing that I was holding on to,
Yep.
and I've drawn the bazooka,
Yep.
and I've drawn the piece of paper,
Yep.
and the hose that leads to the vacuum.
OK, and that's a very, very important picture because particularly Year 7 and 8 children will just concentrate on what the bit of apparatus is. And what we're trying to do in terms of physics teaching is to go a stage beyond that. But you do need that picture. And often people, when they're teaching physics, they leave that picture out and the children get confused. Let me show you what I've drawn. I've drawn 2 pictures. The first shows the projectile. And this is outside and this is inside. And I'm using some graphics here to try and show a pressure difference. This high density of molecule end is outside. This lower density of molecule is inside because I'm evacuating air, at least partially, from the apparatus. I then represent the force due to this pressure by a small arrow inside and a much bigger arrow on the outside. So I've got unbalanced forces. Unbalanced forces produce acceleration.
2 weeks later, David prepares to use some of Steve's ideas with the Year 7 group. Steve and Jifty are observing the lesson from a specially built television-style gallery in one of Barnet's schools, St James's Catholic High School.
We are going to learn why an object floats when it's in a liquid, or some objects float when they're in liquids, and we're going to learn what forces are acting on an object when it's floating. So our learning outcomes, what you should be able to do by the end of the lesson, is you will be able to draw the force arrows on a floating object. You will be able to predict what causes a bubble to rise when it's in a liquid and explain why. And you'll be able to carry out an experiment to investigate how quickly bubbles rise.
David has decided to introduce force arrows, starting with something more familiar to this Year 7 group.
the upthrust can't handle the weight. That's why it sank to the bottom. But these ones, they carry a bit of air, and the upthrust is pushing it up as well because it can handle its reacting with gravity, but that one's just gravity's taking it in.
That's a really good start, isn't
That's
it?
a very good
Yes.
start. And this is a Year 7 group,
Year
isn't it?
7, yeah.
So some of these ideas will be really new
That's right.
for the kids.
They may have come across a little bit about gravity and upthrust, but not about force arrows at all.
In forces, one of the big problems that children have is actually using the arrow idea.
To help students understand these force arrows, Steve showed the teachers a piece of software to use in the classroom. The software allows you to show the forces acting on an object as force arrows, and it even allows you to demonstrate how pressure increases with depth.
Now, forces diagrams are really simple ways of drawing the forces acting on objects, okay? And we simplify them right down. So, for example, if I've got a boat that looks like this, okay, we change the shape of the boat a little bit to make the diagram simpler. What I'd like you to tell me is what forces are acting on that boat.
Upthrust and gravity are
Excellent. So we've got upthrust and we've got gravity acting on the boat. Which directions do they
gravity
act in?
pulls it down and upthrust is pushing it up.
Gravity pulls it down, upthrust pushes it up. Brilliant. So here we've got our force diagrams. Now, on a force diagram, you draw the direction that the forces are acting in with an arrow. So here we've got a green arrow showing gravity pulling down, and the blue arrows, the upthrust pushing the thing up.
In a moment, I'm going to make some air bubbles in this glycerol. Now, glycerol is a very gooey, honey-like liquid. I want you to try and imagine that you're an air bubble inside the glycerol. I want you to draw a force picture of that air bubble.
What we're going to be doing is a little investigation. So can anyone tell me, what do you think is going to happen when I press down on the end of this syringe?
The bubbles, gonna come out.
So we're going to get some bubbles. Bubbles of what?
Air.
Of air. And they're going to go into the solution. What's going to happen to those bubbles when they're in the solution?
They're gonna float up.
They are. They're going to float up towards the surface.
Dave, you've got what looks a phenomenally interesting picture there. OK, I can see an upthrust arrow, I can see a gravity arrow, I can see some pressure arrows. I've got a movement which is not on the diagram, which is on the actual object, which is good. You haven't put any drag force.
Yeah, I haven't labelled it. It should really say gravity and drag, because what I've done is drawn one arrow as a resultant sort of downward force.
The other thing I like about your drawing is that you've shown the sideways pressure, so it means you're thinking about pressure as the root causes the upthrust. But because that's sideways is cancelling out, we would forget that. Richard he's got the pressure business, he's got gravity. What he's done, which is nice, is he's used the ideas we were discussing about buoyancy to explain the upthrust force. But you haven't put any drag force in.
No, but then I thought that initially it would accelerate. It's got to move to create a drag force, and then if I added a drag force, I might actually find that turn into a velocity rather than an acceleration, because they might.
Oh, now that's interesting. Yeah, I think that the point you've made about it accelerating initially is absolutely right, because if you think about it at first, when the bubble's just comes out the end of the tube, and you'll see that in a minute, then you've got the upthrust and you've got the weight, and the weight's not very big because it's just the weight of a little bubble of air. And air is much less dense than the liquid around it. Yeah. So you're right, you may indeed get a situation where the forces come into balance.
We're going to have a think about which bubbles get to the surface fast, whether it's small bubbles or whether it's large bubbles. Okay. I'll blow a bubble and we'll watch it rise. So there's some bubbles coming through. So what factors are going to affect the speed at which the bubble rises?
Which bubble will go up the fastest? And what I'm after here in making a prediction is lots of because words. Okay, it doesn't matter whether they get it right or wrong. It's the thought process that's the important thing.
Well, I think that it'll be the smaller bubble because it is less weight,
and the upthrust will make it go faster. So the bigger the object, the more upthrust there is.
There are lots of factors in play here, so this is a difficult problem to analyse.
I'd like you to suggest for me, please, sir, one factor that can affect how quickly the bubble will rise.
Up thrust, because the bigger the object is, the more there is to up thrust, so it'll go quicker.
So you're saying the size of the object is the size of the bubble in this case is a factor that's going to affect how quickly it rises, yeah? Excellent answer. That's a great suggestion.
The weight of it, if it's heavier, then it won't go up as faster. So the lighter, the more up thrust.
Anybody else? Any other suggestions? Things that could affect how quickly the bubble rises?
A large bubble will go slower because it has more surface area and it's more heavier than a small one.
And a smaller bubble would rise quicker.
Excellent. So we're going to have a quick vote, and I want you to tell me in your groups whether you think the large bubble will reach the surface first or the small bubble will reach the surface first, or whether you think they'll get there at the same time. So can I have hands up, please, if you think the large bubble is going to reach the surface first? Is that one hand or two? Two? Three. Three hands. OK, brilliant. So can you put your hand up if you think the small bubble will reach the surface first? OK, 17 people. And can you put your hand up, please, if you think that both bubbles will get to the surface at the same time? So we've got 5 people that think they'll get to the surface at the same time. It's nice for them to have a misconception and then sort of, address that and think something different by the end of the lesson.
See the big one overtake the little one there? So the next stage is to go back and explore the model again.
What's the force that's pushing the bubble up? What's that force called? Upthrust. So upthrust is caused by something pushing the bubble up.
The water particles.
So why then does a larger bubble rise quicker than a smaller bubble?
Because it needs more particles to push it up. So
which one's getting hit by more particles, little bubble or big bubble? Big bubble, yeah? So the bigger bubble has a larger surface area, which means more particles can hit it, so more particles are pushing it up, so it has a larger upthrust. Okay?
Now, most of them predicted that the little bubbles would race to the top.
That's right.
The fastest, so it would be interesting to see how many of them start to modify what they were thinking.
Can you now put your hand up if you think that a small bubble gets to the surface first? Can you put your hand up if you think a large bubble gets to the surface first? Excellent, brilliant. So what's the most important factor in determining the speed at which the bubble rises?
Size. Having heard some of the explanations, David got one member of each group to present their findings to the class.
The bigger the bubble, it has a bigger surface area and there's more upthrust against it and it just makes it go up faster.
When your bubble was rising, did it carry on getting faster and faster and faster? How did it rise?
Well, with constant speed.
OK, so what can you tell me about the upthrust and the fact of the gravity and the drag that's pulling the force that's pushing the bubble back down?
They're both equally pulling it.
Yeah, they're balanced. Excellent. They're equal and opposite because it's moving at a constant speed.
A lot of children, of course, and you're bound to have met this, will say that the bubble stops moving. What we're saying here then is that the acceleration will gradually come to zero and it will move upwards at a constant speed.
So I think David can feel quite comfortable that he's met the outcomes of that lesson.
Absolutely. And
really.
with an ambitious, sort of quite high order thinking skills type lesson with Year 7s, pretty successful, or very successful.
Very successful lesson.
After Steve's presentation and the work that I'd done with Gifty, I definitely feel more confident teaching this aspect of forces, particularly to this level, and I'm looking forward to teaching it again next year.